In this two-part video, we will be discussing the different types of heat exchangers used in York brand chiller products, how they work, and typical application and maintenance considerations. However, first let's briefly review the purpose of a heat exchanger, which as you can see is simply to transfer or move thermal energy from one source to another. In our industry, heat exchangers are used in many different heating and cooling applications, from enthalpy wheels or mixing boxes and air handling units, to plate and frame heat exchangers used in district energy systems, to residential, commercial, and industrial mechanical cooling equipment. And, specifically for chillers, heat exchangers are used primarily to transfer heat in both air-cooled and water-cooled equipment types, as highlighted. In evaporator applications, heat is moved from the building's chilled water loop to the chiller's refrigerant. And after compression, a condenser is used to move the heat energy from the refrigerant to the ambient environment. And this happens either directly, as with an air-cooled chiller, or through a condenser water loop onto the cooling tower with a water-cooled chiller. Let's discuss the different types of heat exchangers that are used on York chillers and their common application considerations. To start this discussion, it's important to understand the many variables manufacturers consider when selecting the quote-unquote right technology for an application. A handful of those considerations are shown in the image, with the application priority of these variables being driven by regional or global political, economic, and social pressures. Meaning smaller chiller applications may be more concerned with first cost, size, and weight, for example, where larger chiller applications are typically more concerned with variables like efficiency, refrigerant charge, and application flexibility. Keep this in mind as we discuss the heat exchanger types used in York chillers for evaporating, condensing, and heat recovery duties. First, we have the round tube plate fin coil, used for refrigerant condensing with small air-cooled scroll chillers and air-cooled heat pumps, not to mention several other York applications with rooftops and residential units. This heat exchanger type, commonly shortened to tube and fin, has been utilized by the HVAC community for decades. So how does it work? Its operation is quite basic, meaning as compressed refrigerant gas passes through the copper tubes, it's condensed from a hot, high-pressure gas into a lower-pressure liquid, as the ambient air is drawn across the coil by the chiller's fan. Its primary advantages are its robust or proven capabilities, driven from lengthy application experience, and its high flexibility, meaning it can be used for standard comfort cooling or heat pump applications with higher lift requirements. In most situations, coil rows simply need to be added to meet the specified design requirements. Lastly, there are several coil coating and material options available to support local application needs, such as copper fin copper coils and electrostatic epoxy coating, which I'll discuss in more detail shortly. These options are commonly utilized in coastal or harsh industrial environments, where the standard copper aluminum coil would have a higher susceptibility to galvanic corrosion due to their dissimilar metal bond. Regarding coil care, there are no standard maintenance requirements. However, facility owners or operators should monitor fin cleanliness and care for the coils as needed to ensure maximum performance. Dirt and debris built up on the coil will lead to increased chiller energy consumption and reduced capacity, which in some applications will lead to additional chillers being cycled on to meet the building load. Both of these consequences lead to unnecessary owner operating expenses, which we want to help our customers avoid. And to be clear, this is true for any heat exchanger design, not just tube and fin. Lastly, note that our chillers have detailed cleaning procedures and recommendations in our operation and maintenance manuals. However, coil cleanliness needs to be regularly monitored locally, as the local environment will dictate when cleaning needs to occur. Next, we have microchannel condenser coils. Their applications continue to grow, but they're primarily used with larger air-cooled scroll and screw chillers. In these heat exchangers, refrigerant flows through small passages in the condenser channel to follow the same phase change from a gas to a liquid as described with tube and fin coils. One of the key differences between this type and round tube plate fin coils is they are all aluminum construction, meaning the coils, fins, and headers are all a common material. This has the advantage of no dissimilar metal contact, which delivers a very low risk for galvanic corrosion. Additionally, and usually more importantly, microchannel coils deliver more heat transfer per volume of coil compared to round tube plate fin coils. So in practical terms, what does that mean for the customer? Well, this means chillers fitted with these coils will reach higher efficiency levels through better heat transfer. And the microchannel coils are always a single row, meaning there's a lower air pressure drop across the coil, which yields lower condenser fan energy consumption. Furthermore, less refrigerant is needed, up to 50% less in some instances, and chillers will be up to 15% lighter due to the coil material and the reduced refrigerant charges. All of these advantages lead to a premium customer experience through lower energy bills, reduced environmental impact, and likely lower installation expenses, meaning a smaller crane could probably be used for lifting. Additionally, this technology has been used in the HVAC industry for more than a decade, and we, Johnson Controls, now have more than 90,000 microchannel coils installed globally, and we've seen extremely high reliability levels. Lastly, like round tube plate fin coils, microchannel coils have several coating options available, such as the previously mentioned electrostatic epoxy coating, which follows the process shown on the screen to get to the final coil. The E-coat, as it's commonly known, is a baked-on epoxy polymer which extends corrosion resistance up to 6,000 hours per ASTM ratings, all while maintaining premium heat transfer capabilities. Maintenance-wise, there are no regular requirements. However, like any fluid-to-air coil, there's the potential for external fouling due to leaves, dirt, or dust. In this case, cleaning is very easy, with low-pressure, potable water, and if needed, a soft bristle non-metallic brush. Two upkeep advantages with microchannel coils are they are always a single row, meaning it's easier to spray water through them to flush out debris, and due to their design, there is minimal risk of bending fins, as microchannel fins do not extend past the tubes. Both of these mean the owner will spend less time and money cleaning coils, and more time enjoying smaller utility bills due to high efficiency operation. That ends the fluid to air heat exchanger portion of this video.
York, high performance environments for life.